Next talk is from IBM Zurich. Thomas got a bachelor's and PhD in mathematics from University of Warwick in the UK. And then he joined Arithmetica in Warwick in 2005. He did some FPGA design and CAD and EDA. Then he was a co-founder of a startup in the UK for a while. And then he joined IBM Research in Zurich in 2013. He's going to now tell us about the great work that's going on in Zurich. So Thomas, please go ahead.
Thank you very much for the introduction. So yeah, today I'm going to talk about so-called classical machine learning methods and how they might benefit from being deployed at HPC scale. So it's a different twist relative to the previous talk. How do I go forward? There we go. Okay, so just to kick off with a motivation about why this is an interesting topic. So the figure here you see is from the Kaggle Data Science Survey, which was taken in November last year. And this shows you the machine learning methods and algorithm usage per respondents ranked in order. And what we can notice here is that the three top machine learning methods that people are using fall into the category of what are known as classical machine learning methods. So you see here we have linear or logistic regression, decision trees or random forest, and gradient boosting machines. So the questions that I'd like to try to address in this talk is firstly, why do classical machine learning models dominate in many applications? And secondly, which classical machine learning workloads might benefit from being deployed in high-performance computing-like environments? And by that, I mean, very large clusters with high-performance hardware. Okay, so let's talk a bit about this first question. So why is classical machine learning still popular? So I'm sure, as you know, deep neural networks dominate the machine learning research community. And indeed, they have achieved state-of-the-art accuracy on many different tasks, including image classification, natural language processing, as well as speech recognition. However, in many of the industries which IBM deals with, so many of our clients work in financial and retail sectors, we find that classical machine learning techniques are still widely used in production. So the question is why? And that reason is primarily the data itself. So we know that deep learning works very well with data like images, natural language, or speech data. But what our clients come to is very often data that looks like this. So you have a big table, perhaps with, it may have millions or hundreds of millions or even billions of rows. But what's really important here is the columns. So we have a tabular data structure, but we also have what are known as categorical variables. So that is, instead of like a numeric variable representing some value, we have a category, like imagine a zip code, which may have a very high cardinality. So to get deep learning to work well with such data sets requires quite a bit of feature engineering and or embedding extraction of those categorical variables. But there's a fair few classical machine learning methods which work well just out of the box with data like this. And this we think is the primary reason why these methods are still so widely used in the industry today. So the next part of the talk is basically a review of classical machine learning models. Just to give you an idea of the structure here, I'm gonna just briefly go through these 4 different methods. And then I'm gonna talk about distributed training. So how we can, or rather, when do we want to train these models in a distributed setting on a large cluster? And how do we do it? And then I'm going to talk a bit about other workloads related to these models, in particular, hyperparameter tuning. So training is not the only compute intensive workload related to these models. Okay, so let's get started with this short review. So the first category of models I'd like to talk about are what are known as generalized linear models. This encompasses quite a few different widely used techniques. If you can recall from the first slide, this is the #1 most used machine learning model by data science practitioners today. Generalized linear models can be used for both classification, so you've probably heard of support vector machines and logistic regression, as well as real valued regression. Depending on how you set the regularization term, you can have what's known as ridge regression, or if you want to have some kind of sparsity in the model, you would use a lasso regression. So what's good about these models? Why do people still use them? The first is that they're very simple and they're very fast. So they can be trained quickly, that the inference is extremely quick. And kind of a secondary reason for that is that they can be scaled to very huge data sets. I mean, like data sets with billions of rows. And I'm going to talk a bit more about that later in the talk. Another good benefit is they're easy to interpret, especially if you put some kind of sparse regularization, which enforces that most of the model coefficients should be 0. This is important in regulated industries where you may need your model to be able to provide an explanation of why your model came to a decision. Another good benefit is that they have very few hyperparameters relative to more complex models. This means that the time required to tune the model is dramatically lower. However, they have some very significant downsides too. So firstly, clearly kind of by the name, you can see that they can't learn nonlinear relationships between features. If you want to do that, you need to do extensive feature engineering. So that's the only way to get linear models to capture that kind of relationship. Many people still do that, but it requires a data scientist to spend a lot of time investigating different combinations, maybe some domain knowledge, and things like that. Okay, so the next class of models, which is really the building block for what comes later, is decision trees. And this really, I want to stress this relationship back to the categorical variables that I mentioned in the beginning. So decision trees is basically a decision tree model is like a hierarchy of rules, where each rule is some kind of test on a feature of the data set. So in this example on the screen, you see a root node where we compare the age feature and we say, is it greater than 30? So if the example is bigger than 30, we go to the left and we reach a leaf node, which has the label +1. On the other hand, if we follow the right branch, we get to a child node, and this child node is a test on a categorical variable. We say, is the zip code equal to 8050? If it is, we label the thing -1. Otherwise, we label the example +1. So here you see already a mixture of numeric and categorical tests, which are one of the reasons why decision trees are a very powerful building block for more complicated models. So just going through again the pros of these models. So they're simple and fast. They're perhaps even better to interpret than a linear model. A human can look at a decision tree and it maps quite well to the way they kind of make decisions too. It's very effective at capturing nonlinear relationships between features, and it has this native support for categorical variables. The downsides. The training algorithm for decision trees is very greedy. It's not really theoretically justified in a sense. Like, with deep learning or other things, you have a loss function, which you're explicitly minimizing. In decision trees, you have a local loss function at each node, which you're minimizing, but you're not really guaranteed to converge to any kind of global optimum. So they're not very nice in a theoretical sense. And they can easily overfit the training data. In a sense, this is actually a pro. This is part of their power. So if you grow a decision tree to unbounded depth, you can easily overfit any data set. So they have a very high capacity, but they're going to generalize very badly to new examples. But this is the kind of problem which we solve with ensemble techniques, which I'm going to take you through next. So the first way to kind of overcome this problem of decision trees overfitting is what's known as random forests. So this is a fairly old technique where you build an ensemble of decision trees. So in this example, we have n different trees. Each one is trained using what's known as a bootstrap sample of the training set. So that's a sample. If you have a training set with n examples, we take a sample of n examples with replacement from the training set. So each tree is trained with a significantly different bootstrap sample of the data. And then when we do inference, we take the prediction from all of the trees and we average it in some way. That might be majority voting for classification. It might be just averaging for regression. But either way, we combine the prediction from all of the trees to get our final result. And in this way, because each tree has a different training set, and furthermore, the trees are randomized in a secondary way by randomly selecting the features of each node, we can reduce the variance of a decision tree estimator. Therefore, we have that big capacity and ability to overfit, but we can also ensure that the model can generalize well. So just to recap, the random forests inherit all of the benefits or most of the benefits of decision trees. In particular, they can deal with categorical variables very well. We massively improve the generalization capability by this bootstrap sampling and averaging. A kind of systems, a systems aspect of random forest, which is very nice, is that they're embarrassingly parallel. So every tree can be trained independently, and we'll talk a bit more about that later. On the downside, they're somewhat heuristic again. With random forests, we're never really explicitly optimizing something. We're just building a bunch of trees and averaging them. There's no explicit optimization happening. They're computationally intense. So to get the best generalization capability, you might need to use things with 1,000 trees or more, which is, even though it's embarrassingly parallel, still requires a lot of computational resources. And they're harder to interpret. So, I mean, this benefit of decision trees is kind of lost. It's very easy to look at one tree and say, this is why the model came to the decision. It's much harder to look at 1,000 and come to the same conclusion. But they do admit some form of interpretability in that you can identify which features are important and so on. Okay, so the final model I'd like to talk about is gradient boosting machines. This is another way to create an ensemble of trees, but it's extremely different to random forests, fundamentally different. So in this figure, which you see on the screen, this illustrates how boosting works in quite a nice way, I think. So we start in the lower left with the first tree, which we fit to the training set. We then make predictions with that tree, and we compute this R1, which is the difference between the labels and the predictions from the first tree. So we call this R1 the residuals. So this is like the errors which the first tree made. We then send those errors as labels into the second tree. So the second tree tries to kind of correct where the first tree made mistakes. And we repeat this n or so times, building an ensemble of n different decision trees. Each one is trying to correct the mistakes of those which came previously. There are many other interpretations of boosting, but this is perhaps the easiest to understand. And this is an extremely powerful method. So some of the reasons why these are very popular today is, again, we inherit many benefits from decision trees, in particular, the ability to deal with categoricals. These methods achieved state-of-the-art generalization on these kind of tabular data sets, and that's why if you look at the winning solution of a vast majority of Kaggle competitions or so on, you'll see the gradient boosting machines being used in some way. And the training algorithm of boosting machines has a very nice theoretical interpretation. So unlike random forests and standalone trees, which is somewhat heuristic, gradient boosting can be interpreted in a way that you're really explicitly optimizing some loss function, which is a very nice property. On the other hand, they're very computationally intense. Again, like random forests, we sometimes need to have thousands of trees or even tens of thousands of trees to get the best performance. And unlike random forests, which I hope is clear from this figure, they're inherently sequential, so they're harder to parallelize. Again, we kind of lose this interpretability that we got from a single tree. And perhaps the thing I'd like to focus on later in the presentation here is that they have a huge number of hyperparameters. So the effort required to tune these models is definitely the highest out of any of the so-called classical machine learning techniques. Okay, very good. So this is the next part of the talk on distributed training. So in this section, I'd like to kind of focus on the difference between data parallel and model parallel training. So two different scenarios of when we want to scale out the training of these models on a large cluster of machines. So yeah, the first question I'd like to address is, why do we want to scale out? The first scenario is when we have very huge data sets. So let's say we have a data set which is like 1 terabyte on disk. So this data set, unless we have some extremely huge server, it can't fit inside the memory of a single node. It's also probably stored in a distributed file system to begin with. So it's a kind of distributed in place. And in this scenario, data parallel training algorithms are really a necessity, even for relatively simple linear models. So in this kind of scenario, we're not choosing to scale out training. We actually need to scale out training no matter what. In the second scenario, we may have a relatively small data set, which can fit inside the memory of a single node, but we might have a very complex model. So we might have, for instance, a random forest with 10,000 trees. In this case, we know there's a high degree of parallelism there, so we would like to scale out the training algorithm, kind of partitioning the model across each node to speed up the training. So we don't have to, but we would like to. So yeah, we're going to consider two different examples of the above scenarios, and at the end, kind of a mixture of the two. All right, so yeah, the first thing I'd like to talk about is the first scenario where we have a very huge data set and we want to train a relatively simple model, so a generalized linear model. So training GLMs, I'm not going to spend too much time on the theoretical aspects here. I just want to kind of draw your attention to a few things. So training a GLM involves some kind of optimization. So we have this alpha, which denotes the model vector, which we would like to learn. And A denotes the data matrix, which is our training data. And F and G are convex functions which specify the loss and the regularization. So this formulation covers, I mean, by selecting different F and G, can cover all of these different cases I mentioned in the beginning, like logistic regression, lasso, ridge, and so on. So in this context, we have to assume that this data matrix A is partitioned across a set of worker machines. And I'll talk a bit about how it should be partitioned later. but it must be partitioned in some way because it doesn't fit in memory. So one approach which one might use to solve the optimization problem is using the standard techniques that people use in deep learning. So in particular, mini-batch stochastic gradient descent. So that's where you would take the gradient of the above expression with respect to a mini-batch of examples, and that mini-batch may be distributed across your cluster. You would then aggregate the gradients with some all-reduce operation, and then take a gradient step in the model. So this works great for deep learning. People have, with some tricks, shown very strong scaling up to, I think, even like thousands of GPUs now. But for linear models, it doesn't work very well. And the reason for that is that the cost of computing the gradients for these kinds of models is typically relatively cheap compared to the cost of communication over the network. So of course, you can solve that by using a larger and larger and larger mini batch, but that typically slows down the convergence in an unfavorable way. So you end up having to do more epochs than you otherwise would. So for that reason, the mini batch SGD has been shown not to be state of the art on problems like this. And I'd like to talk a bit about what people do in this context and what are the methods people use. So yeah, the first thing I'd like to talk about is this Cocoa framework. So this is a different way to solve generalized linear models in the distributed or scale out setting. So let's for a minute assume that our data matrix A has been partitioned across the workers by column. So each worker node contains a subset of the columns of the data matrix. So we can obviously shuffle them. So it's not necessarily a sequential partition, but they can be shuffled across the cluster. So the Cocoa framework, which was in a paper from 2018, I think there was actually some earlier, but this is the long one, defines a data local subproblem, which can be solved like locally on each worker. So this equation that you see here, kind of, I'm not going to describe the details of the subproblem, just what it depends on. So here we have a minimization problem over this alpha k, and this alpha k denotes the local coordinates. So if we think about the partitioning again, the model consists of a value we would like to learn for each feature, and we've distributed the data set by feature across the cluster. So each worker would like to solve this optimization problem with respect to the features to which it's been assigned. And this data local subproblem depends on this A of k, which denotes the columns of the kth worker which it's been assigned, as well as the previous values of the model, and this v. And this v is some shared state which needs to be communicated intermittently between the workers on the cluster. And I'm going to give some examples of how that works shortly after this slide. So one of the nice things about the Cocoa framework is it doesn't really specify which algorithm you could use. So all you have to do is solve, in each round of communication, you have to solve this data local subproblem in some approximate way. So that means you could use stochastic gradient descent. You could use methods based on stochastic coordinate descent, which are very popular for these kinds of models. Or you could use methods which run effectively on the GPU, and so on. It's a very general framework. So yeah, once we solve this in an approximate way, we update this shared state across all of the workers, and then the process repeats. And I'm going to show an illustration of that on the next chart. So yeah, this method is guaranteed to converge in a theoretical sense, and it allows us to trade off this ratio of computation against communication much more effectively than mini-batch SGD does. So just to give you kind of a walkthrough of how it works. So we start in this example with 3 workers. So each one has its own partition of the data. Then we execute this local solver, which is making an approximate solution to this data local subproblem. And this local solver produces two things on each node. It produces the updates to the local model. So there's alpha 0, alpha 1, alpha 2, alpha 3. If we concatenate those vectors, we have our global model. And we have this V, which is local to each worker. So each local solver produces some sort of updated version of V. Now, this V needs to be communicated. So the way which this is most effectively done is using an all-reduced primitive. So we can do this in MPI very easily. And after we do the all-reduced, we have our new state V, which we can then take forward into the next round. So we put the local coordinates, go into the local solver, as well as the new shared state V, and the process repeats. So one of the questions here is, how big is V? Clearly, the communication is going to scale like with the dimension of V. So for which kinds of problems is V small and which kinds of problems is V very large? So here we come to a very a secondary property, which is extremely nice for these kinds of problems. And that is that we have two different formulations of many GLM problems. The typical one is known as the primal, which is kind of shown in red here. So we have some surface, some convex surface that we're trying to optimize by finding the minimum. We can express the problem as an equivalent dual optimization problem, where we have some dual surface, which we're trying to maximize. So what's the difference between these two? Cocoa can handle either, which is one very nice property. The question is, when would we like to use the primal and when would we like to use the dual? So in the primal case, which is kind of the normal way which machine learning problems are formulated, as I mentioned earlier, we partition the data by column across the cluster. So each worker has a subset of the data features. And the model vector alpha has dimension m, where m is the number of features. And the shared state V has dimension n, where n is the number of examples. So if we have a data set where the number of features is huge relative to the number of examples, then the primal case of when we use Cocoa makes a lot of sense, because the communication is going to scale like ON, and we're not going to have to transfer huge vectors. In the alternative case, where we have the dual problem, we would partition the data by example. So each worker has a subset of the examples of the training data. And the model vector now has dimension n. So we have a kind of model value for each example. And the shared state V has dimension m, the number of features. So in the case where we have data sets which have, many more examples than features, the opposite case, the dual makes much more sense for distributed training. So this is one really nice property of Cocoa, which allows us to minimize communication for extremely asymmetric data sets. So just to give you a real example, which is some of the work which we've been doing in my lab, this is for a data set. It's a popular benchmark for distributed machine learning, which is this Criteo terabyte click logs. So this is like a advertising click-through rate application. It has 4 billion examples, and depending on how you do the features, I think in this case we have around 1 million features. And we're trying to train a relatively simple model, a logistic regression model. And it turns out this is something that many people have tried to do in the past on this data set and have published their training time as well as the accuracy on the test set which they achieved. And that's what you see here. So on the x-axis is the logarithmic training time in minutes. And on the y-axis is the logistic loss on the test set. So there's a bunch of different things here. I'd like to focus on some of them. So the first two, which I've highlighted here, Spark, MLlib, and TensorFlow on Spark. The hardware used in these cases is different. So it's not really an apples to apples comparison, except two, which I'll discuss a bit later. But what you can see here is that the Spark, both of these Spark ones use mini batch SGD, and they're fairly slow relative to the fastest approach, and they also don't converge, they don't achieve the same accuracy. So they haven't converged as well to the optimum of this problem. So all of the model parameters are the same and so on, but we are not getting the same generalization accuracy. So these three approaches, which I've highlighted here, are all using Cocoa. So TensorFlow uses Cocoa natively for training of distributed training of logistic regression. It has that functionality. You can also do it other ways, as shown above. So the orange point here is a data point which Google published on their blog. So they use their Google Cloud platform, and they use something like 60 worker machines plus 30 parameter server machines to solve this task. And they can do it in around 70 minutes or so. Then the other 2 points are measurements which we took on our own cluster here. So the one on the right is TensorFlow using 16 V100 GPUs. So you can see it's actually slower than the kind of around 90 CPU-based machines. And on the left is the framework which we developed in our team in the lab in Zurich. So this is SnapML, which I'm not going to talk in detail about that in this presentation because I don't want to make an advert. But you can go and read about it if you're more interested. This uses a variant of Cocoa, as well as new algorithms for effectively using the GPUs and a very efficient MPI-based implementation. So we're kind of using HPC like approaches to implement this kind of algorithm. So you see that in the blue and the green case, we can really compare like apples to apples on the same hardware, and we're doing much better than, any of the other data points here. So that's kind of all I wanted to say about the generalized linear models. I'd like to move on to talk about a different use case for distributed training, which is random forest. So as you can imagine, random forests are at first glance a bit simpler. So let's consider the case where the data set fits in the memory of a single node. So we have, I don't know, 10 gigabyte data set. So in order to train, let's say we have a huge random forest that we want to train, like 4,000 trees. So the first thing we can do is to replicate the training data across the cluster. So each worker will have a replica of the training data set. And we just partition the trees across the machines. So let's say we have 4,000 trees. Worker 0 will train the first 1,000, worker 1 the next 1,000, and so on. So it's embarrassingly parallel. We would expect if the model is large enough, so if we increase the number of trees as much as you want, you should be able to see linear speedups. Yeah, because it's embarrassingly parallel. So any overheads which exist should be eventually squashed by the amount of computation you have to do. So indeed, that's more or less what we see. So this is just some data showing the training speed up relative to kind of the ideal case for 50, 100, 200, and 400 trees. And we see that as we keep increasing the number of trees, we're getting closer and closer and closer to that ideal curve. As I mentioned at the beginning, you do see improving accuracy up to 1,000 or even 10,000 trees in the forest. So there's a lot of potential there for speeding up training really in production. What about the kind of combination of the two scenarios that I mentioned before? So what if we have, as well as a big model, what if we have a data set that's too large to fit in the memory of a single node? So kind of the combination of the first example I showed and the second example. So let's imagine training a random forest in this sort of scenario where we have a data partition on each cluster. So the straightforward way to do random forest would be to train every tree in a distributed way. So we would start with tree 0 and we would build it across all workers, move on to tree 1. But of course, to do that, we require a lot of communication across the network. Tree building is quite a intensive task. You need to communicate lots of information about which features are split, which nodes contain which examples, and so on. So people start to look about how could we do this in a more data parallel way? Is there a way we could do it, change the algorithm to better fit the kind of scale out scenario? So that's what I call here data parallel plus model parallel random forest, which is something that people have been looking at quite recently. You can find it implemented in some of the popular frameworks. So I mentioned in the beginning that in a random forest, you improve the generalization by training each tree on a bootstrap sample of the training data. So that is, every tree is trained on a kind of a sampling with replacement from the training data matrix. So what if we relax that constraint? So what if instead we say, okay, we're going to partition the data into 4, 16, 32 partitions, and we're going to train each tree on a partition instead. So clearly this reduces the amount of data in each tree, but it's only a relatively minor modification to the random forest algorithm as specified. So let's consider how that would look. So we go back to this use case where the data is kind of distributed in place. So we have 4 data partitions across workers. So we would then train a partition of the trees independently on each partition of the data. So in this case, we've partitioned the data set and we've partitioned the model. So we would actually expect super linear scaling here. So for big enough data and big enough model, we would get, for 4 workers, we would get a factor of 4 from distributing the data times another factor of 4 from distributing the trees. So this is from a kind of systems point of view, something really nice. But the question is, do we lose something? So we really changed the algorithm. Instead of using a bootstrap sample for every tree, we're using a partition. And that's what I'd like to show in this figure. So this is some experiments that we did on a real retail use case. So this is this Rossmann store sales. It's actually a Kaggle competition. It has around 800K examples and 20 features. So it's not an enormous data set, but still on the large side. So we train here a random forest with 100 trees. Each tree has depth 8. And we do 10 repetitions with a different random seed each time, because the random forest is inherently random in many different ways. So to evaluate the performance, we need to see the average and the standard deviation, which is what you see on this figure. So on the x-axis, we have the number of partitions. So it's on a log scale. It goes from 1 partition up to 128. And on the y-axis is the generalization performance. So the metric here is this root mean squared percentage error. So what we see is that the accuracy degrades fairly slowly up to around 10 partitions, but then gets pretty bad as we go up to 100 partitions. So it starts degrading much more quickly. So this is, as I mentioned, this is a relatively small data set. So it may be that if you go to data sets with billions of examples, this curve looks different. So actually, I think it's a fairly promising result, which indicates that this, I mean, for this size of data, probably using around 16 partitions is already going to get you a very big improvement. So for larger data sets with, terascale, it may be that we can go out to, 100 or 1,000, say, MPI processes, each training partition of trees on a partition of the data and still get a relatively good accuracy. Okay, so moving on to the last part of the talk, which is about hyperparameter tuning. I think we're more or less on time here. So I'd like to go back to the last class of models, which I mentioned, which are gradient boosting machines. So these machines have a very large number of hyperparameters. I'm not going to explain them all, but here are some examples. We have the number of boosting rounds, the learning rate, the subsampling rates at each round, the tree depth, as well as regularization penalties. There's even more, but these are the ones that people commonly look to tune. So the normal way you do this is you split your training set into an effective training set and a validation set. And you use the validation set to evaluate the accuracy of different choices of hyperparameters. So this is what's known as hyperparameter tuning, and there exist many different algorithms. All of them involve evaluating a very large number, say like thousands of different configurations. So what I'd like to kind of highlight here is that hyperparameter tuning can lead to HPC scale workloads, even for relatively small data sets. So I'm going to focus on three popular methods which people use to do hyperparameter tuning. And I picked these methods for a reason, that they have they admit a high degree of parallelism. There are other methods which there's a huge field around, say, Bayesian optimization. I'm not focusing on that here because it's much harder to deploy in kind of extremely, on an extremely large cluster. All right, so the first is random search, which many people should know. It's probably the simplest method for hyperparameter tuning. It works like as follows. So you draw n hyperparameter configurations at random. You train each one on the training set, and you evaluate or score each one on the validation set. So you measure your loss function. That might be logistic loss, the 0-1 loss, or it might be something else like the ROC AUC score. And then to select the winner, we pick the configuration that gives us the lowest score on the validation set, or the highest, depending on which metric you choose. So clearly, random search is embarrassingly parallel. So every single hyperparameter evaluation is independent. So it can be very, very effectively parallelized across huge clusters of machines. I would add one small tip if you're planning to do this, that an optimal implementation requires a little bit of thought, because especially for, say, boosting machines, different configurations may take much longer to train than others, depending on which. Some hyperparameters have no effect on the runtime, but some have like a very strong impact on the runtime. So it's important to bear that in mind when writing some code to do this. So yeah, I would say avoid doing things like batch synchronization. Maybe asynchronous approaches work better. So even though this is extremely simple baseline, it's widely acknowledged that random search is pretty hard to beat, especially when you have very high dimensional problems. But there's a whole research field of trying to do that, and there's many different ways people try. So the first I'd like to discuss is something called successive halving. So as you could imagine, random search will waste a lot of time training and evaluating configurations which are no good at all. So how might we improve that? So could we think of a way to discard bad configurations more quickly? And that's basically what successive halving tries to do by introducing the notion of a resource. So the resource can be application dependent. Some examples here are the number of gradient descent steps, say if you're doing SGD, or the number of boosting rounds if you're doing gradient boosting, that's like the number of trees in the ensemble. Or it could be in a model independent resource would be the size of a random sample of the training data set. So you could say my resource is the amount of data I'm going to train on. The important thing is that when you make the resource small, the training is faster. That's the kind of thing you're looking for when you define this resource. So the main idea of successive halving is that we should evaluate a very large number of configurations quickly using a small resource and carry forward only the best ones for evaluation with a larger resource. And I have a kind of walked example here. So we start by drawing N0 configurations at random, just like in random search actually. Then we evaluate fully in parallel, so we can scale out across as many nodes in the cluster as you have, using an initial resource R0. So this could be, as I said, it might be just a very tiny subset of the data. So this should be relatively quick. And once we've done that, we're going to take the best N1 configuration. And what you see here is that N1 is given by N0 divided by eta. So eta is the kind of halving parameter. So if you think about successive halving in its kind of named sense, eta would be equal to 2. So we're looking for the top half of configurations to take forward into the next round. So in the next round, we take the N0 divided by eta configurations, and we evaluate them with a new resource R1, which is eta times bigger than R0. So in each round, what you might see here is that we're multiplying the resource by a factor of eta and reducing the number of configurations by a factor of eta as well. So in the next case, we make N2, we take the top N2 configurations by dividing N1 again by eta. And we keep going until we reach some maximum resource which can be user defined. Let's say 1,000 trees. And then we take the best NS configurations, and then we take the best of all of them. We take the best one we found across the whole course of the successive halving, and that's our output. So when does this work well and when does it not? This is a figure from a paper we did with a student working in our lab. And on the left-hand side, you see the kind of ideal case for successive halving. So each gray line indicates the trajectory of a different hyperparameter configuration as a function of the resource, which in this case is the number of trees in a gradient boosting machine. And on the y-axis is the validation loss. Each vertical black line indicates the round of successive halving. The highlighted red configurations are those that we keep as we go from round to round to round. So you see in the beginning, we have a lot of red ones, then we gradually reduce until we have only one in the end. So in this figure, it's the ideal case for successive halving. So what you see is that the configuration which works best in the final round also worked well in the first round. So we can identify that configuration from the beginning. However, in the figure on the right-hand side, the opposite is true. So we see that successive halving fails to identify the best configuration because the configuration which looks good at the end was actually discarded in the first round because it was in the worst half of the configurations. So this is an inherent problem of successive halving. There's not really any way to solve it with the algorithm itself. Successive halving is built on the idea that good configurations can be identified with a very small resource. So how might we solve that? And that's what the paper with the algorithm Hyperband tries to do from 2018. Again, it's very simple. These are not complicated algorithms to implement. We create multiple, what's known as brackets of successive halving. So each bracket gets progressively more exploitative rather than explorative. So what do I mean by that? Explorative, we mean we're going to evaluate a lot of configurations with a small resource. Exploitative means we're going to evaluate fewer configurations with a large resource. So here's an example for quite an extreme setup of successive halving. So we have, this is a typo, sorry. Eta is 10 in this example, and R is 100. Let's quickly change that. Okay, this is correct. So we see these three brackets. So in the first one, we start with 100 configurations and resource 1. In the next round, we reduce the number of configurations by a factor of 10 and increase the resource by a factor of 10. And in the second round, we do the same. So at the end, we have one configuration with max resource 100. In the next bracket, we start with a fewer number of configurations, 15, and we start with a bigger resource. We start with resource 10. And in the final bracket, we have 3 configurations with the maximum resource. So bracket 2 is basically equivalent to random search. And the numbers, the kind of exact numbers you see here, are designed so that the total amount of resource evaluated in each bracket is roughly the same, up to the problem with like integer division that you have. So the Hyperband algorithm is very simple. You run all brackets in parallel and output the best configuration that you found. So going back to that bad example that I showed, bracket 0 is very susceptible to that because the resource in the beginning is so small. Bracket 1, whereas bracket 2 is like random search. We always evaluate every configuration using all of the data. But bracket 1 is somewhere in between. So it might be that when you use resource 10, you can already pull out the good configurations, which otherwise would have been impossible to identify with resource 1. So it's kind of a fairly direct way to try and solve this problem, and it also massively increases the amount of parallelism that you have, because not only can all of the configurations within each round be executed in parallel on a cluster, you also have parallelism at the bracket level. So you can distribute every bracket fully independently. So just to show an example, which is actually from their paper. So this is the application of Hyperband to the HPT task for a kernel-based classifier on the Cypher-10 dataset. In the kind of green curve here, you see the random search with the equivalent budget. That means the equivalent like resource given, as well as random search with twice the budget. And in the yellow line is the performance of Hyperband. And you also have on here in red and blue the performance of 2 popular Bayesian optimization techniques. So we see that Hyperband significantly outperforms random search, and it outperforms these Bayesian optimization techniques. And I'm not going to go into much detail about that. They're popular, but they're much harder to parallelize. So if we're thinking about how we might use HPC scale infrastructure to do hyperparameter tuning, I'd be much more inclined to suggest following the approach of Hyperband or successive halving rather than going the Bayesian optimization route. Okay, so that brings me to the end of the presentation. Just to conclude quickly, classical machine learning methods are still very popular in domains where tabular data is abundant. Training can be distributed across a very large cluster when either we have a huge data set and a simple model, or a small data set and a complex model, or both. And for models like gradient boosting machines, which have a very large number of hyperparameters, the tuning task can become extremely computationally intense, even when we have tiny data sets. So recent advances in highly parallel HPT algorithms show a lot of promise in this HPC scale environment. Okay, so that's the end of my talk. I'm happy to take any questions. And I'd just like to mention quickly, yeah, I work in our research lab in Zurich. It's a very nice location. As you can see, we're always interested in hearing from intern students, master's thesis students, or postdocs. So please get in touch if you're looking for any of those positions.
Yeah. Thank you very much, Thomas. It's very interesting. Wow, we have a bunch of questions. Okay, Yunho. Go ahead. We can't hear you, Yunho. Okay, let's go with Mario so that Yunho fixes his microphone.
All right. So can you hear me?
Yep.
Okay, good. My question is in the successive halving algorithm.
Yep.
Have you tried like backtracking? So maybe if you go back and you reuse some of the ones that did not work very well in the early stages, you can get back on track.
That's not something that we've tried. We've tried quite a few different things to try and fix that problem. We haven't looked at like backtracking. I haven't seen any papers doing that. One of the ways we tried to do it was using what's called meta learning. So if we kind of know from past experience that one configuration worked really well on a bunch of different data sets, that maybe we shouldn't exclude that, we should take it forward. But that's a kind of orthogonal idea. But yeah, potentially that's an interesting idea.
Okay, thanks.
Okay, Yunho, can we hear you? All right, let me ask a quick question too. So this is more of an uninformed question. So this is a question from somebody who has not been in AI in a long time. When I look at your graphs and your performance is basically either time on the x-axis or accuracy on the y-axis. I noticed that the goal for you is to try to reduce the amount of resources while you beat the accuracy of others. In this case, the test errors were dropping up to 0.4 and then they were leveling. And I was wondering, for the applications that you're looking at, is there a bare minimum threshold for what the test accuracy or the test error should be? Because otherwise, just reducing the time to get there is not very helpful.
Right. So yeah, the answer is no. I think in general there isn't. This figure I showed here is a bit of a special case. Let me just see. Yeah, like this one here is a bit of a special case because this is a generalized linear model. So the model is the same in all cases, and the generalized linear model has a unique solution. So in fact, regardless of the hardware you use, regardless of the software framework, all models should be able to find the best solution if they've converged. So in principle, if you ran the Spark ones for longer, they should eventually get to exactly the same log loss. So this is like purely a comparison of like resources and time. So the model is the same in all cases. That's not really a typical situation. I mean, if you're comparing different models with different hyperparameters, yeah, it's much more complicated to make these kinds of comparisons. You have to always make sure you've tuned all of the hyperparameters carefully in order to make an apples to apples comparison. But I wouldn't say there's ever any kind of baseline error that you can expect. It entirely depends on the data set, entirely depends on the model that you're using.
Okay, thank you very much. Any other questions? All right. Well, thank you very much, Thomas, for this wonderful talk. I just, before we break off for the virtual the Slack meetings for the posters, I wanted to announce that NVIDIA is actually hosting their annual convention GTC online, and it's available to all of you for free. I will post the link on the chat window for you to see the link so you can participate. That was just a message from Gunter and the NVIDIA team. So we're gonna break up. We have, I believe, a 1 hour window. So we'll be back for our last talk from HPE. Paula Farabuski is a VP at HPE who is gonna tell us about AI infrastructure at HPE. So please go to the Slack channel. There's a lot of activity on those posters and we look forward to seeing you there.